Hello and welcome to another video in the graph series. A very important topic in graphs is cycles. It is also a major difference between graphs and trees. Graphs can have cycles, trees cannot. So obviously a very important question becomes how to detect cycles in graphs. Now this concept is different for directed and undirected graphs, and it is very important that you understand the difference between the two. A lot of people make this mistake. They focus just on detecting cycles in indirected graphs or directed graphs, and then they end up getting confused later that what was the difference between them? Why are these two solutions different? So it is very important that we understand the concepts today, that we understand the intuition behind both the questions today and understand it why they are different. So that is what we'll be doing today, focusing on concepts, and there'll be a lot of follow-up questions based on this particular topic in the coming up videos. So make sure you watch those videos. We'll be writing the code in both C++ and Java, and let's get started. Before we move ahead, I would just like to take a moment to remind you to be consistent and make sure you do not miss any videos in the graph series. So make sure you subscribe, hit the notification bell icon. You will also stay motivated, and you have no idea how much your support will mean to me. There's so much of free content available on the channel. There's HLD, LLD, DSA, Advanced C++, tutorials, mock interviews, and so much more. So if you think I deserve your support, please subscribe, hit the notification bell icon. And there's obviously a bunch of stuff that I cannot do on YouTube, like mock interviews, live interactive classes. So we have educourses.com. We have live courses, self-paced courses with live doubt solving support, which both of them we have mock interviews, and we have a lot planned in LLD, HLD, Advanced C++, DSA, and so much more. You have no idea. So if you want me to be part of your further learning journey process, please check it out. The link is in the description. And now let's continue. As you can see, I have made some random graphs over here. Now, if you had to start thinking that how would you detect cycles in a graph? Now, you would think that there is one concept that we have been repeatedly thinking about in graphs, which is basically visited array, right? And we have been thinking about that visited array or visited set. Why? To avoid cycles. Now that has been a major reason, and we have been doing this repeatedly, that we take a visited array or set to avoid cycles. So does that mean that if we just take a visited set, does that solve our problems or not? Let's see. But that would mean that the solution is actually very easy. Then why do we need to go through concepts? Let's actually see, because there's a small tricky point over here. So if I get started from here, I mark it as visited. Then I go to its neighbors, I mark this as visited. I mark this as visited. And then when I come back over here and I see, oh, this has already been visited, does that mean that there's a cycle? Let's see. Can we do it so simply? So if I mark this as visited, I mark this as visited, I mark this as visited. When I come back over here, there's a cycle. That seems very easy, right? Similarly, in this example, I can start from any node. I mark this as visited, this is visited, this is visited, this is visited, this is visited. Now, when I come from here again, I see that this has already been visited. That means there's a cycle. Now, this seems like very obvious thing, right? Now, this is also visited, this is also visited, 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 visited. When you come back here, oh, there's a cycle. No, very simple. But what is the tricky point over here? See, the thing is that how do we represent graphs? Let's come back to the basics. Let's say the nodes were numbered 1, 2, and 3. So how do we represent this graph? 1 is connected to 2 and 3. 2 is connected to 1 and 3. And 3 is connected to 1 and 2. Now, the problem over here is that when we start from a particular node, so suppose we go from 1 to 2, and then we go from 2 to 3, and then we go from 3 to 1, we do not know from where we are coming. And now to understand this point, just look at this very small change that I am making. I am removing this edge. That means there is no cycle now, correct? So how does our adjacency list change? So let's think about this. So 1 is connected to 2, 2 is connected to 1, and 3 is connected to 1. Correct? 1 is connected to 2 and 3. So 1 is connected to 2 and 3, right? So this is how our adjacency list looks like. Now let's see that if we had to detect cycle in this, what would we do? So suppose I start from 1, I mark it as visited, that okay, this has been visited. So 1 is visited. I go to its neighbors. So I first come to 2, and then I see that okay, 2 is connected to 1, right? 2 is connected to 1. And then I come back over here and see, oh, 1 is visited. So there is no cycle over here. So basically what is happening is that I mark 1 as visited, I go to 2, and then I had already marked 2 as visited. Now I come back to 1 and I see, oh, this is visited. So basically I am in a forever loop, visited, 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 like that, right? And it is possible, right? So somehow I need a way that, the node from which I am coming, I should not consider that while marking the neighbors as visited. This is a very interesting point. Let me explain this once more. So suppose we have two nodes, 1 and 2. We are at 1 now, so we mark this as visited. When we go from 1 to 2, we mark this as visited. Now the thing is that both 1 and 2 are marked. Now we want to start considering 2's neighbors. Suppose there were some neighbors of 2 like this, okay, 3, 4, 5. The thing is that when I start exploring the neighbors of 2, we are again considering 1 as well. So basically I should consider the neighbors of 2, but I should avoid the node from where we came. Correct? Because this does not mean that there's a cycle. We are actually coming from there. So that is why in a lot of cases, in a lot of solutions for graphs, you will see a concept of parent. And you might get a bit confused because parents are there in trees, not in graphs, right? Because there is basically a parent and there are children. That's how a tree looks like. Why do we say parent in graphs? In very simple term, it is just the node from which you are coming. Like while traversing, that is the node from which you are coming. So very, very simple. Let's try run this once more so that it is completely clear and you will not get confused at all. Before we dry run, it is very, very important to understand that again, we are just traversing over here. Now we can be traversing using DFS or BFS. So we can detect cycles using both DFS and BFS. Let's get started with DFS first. So suppose I have this one graph, as you can see. So this is one huge graph. As you can see, it has two disconnected components. So if you can see, this is one component and this is the other component. Okay. Now let's talk about how would you represent this graph in an adjacency list. So 1 is connected to 2 and 3, 2 is connected to 1, 3 is connected to 1, 4 is connected to 5, 6, 5 is connected to 4 and 6 is connected to 4 and 5. Correct? Now suppose let's start from 1. So whenever I start from a particular node, I see that who is the parent. Now I'm starting from here, I'm not going from anywhere. So suppose the parent that I am passing, I can pass it as anything. I can pass it as -1 because I'm not coming from anywhere, right? So -1 cannot be a possible value. This means that this is my source node from where I'm starting my traversal, right? So my parent is -1. I come over here, I mark 1 as visited. I come to the adjacency list and I see who are the neighbors of 1. So who are the neighbors of 1? It is 2 and 3. So suppose now 1 was marked as visited. So suppose I mark 2 as visited. I see now who are the neighbors of 2. I go to 2. When I go to 2, who is the parent of 2? My parent of 2 now is 1. Correct? So in that function, what I'll be passing, I'm doing using DFS. So there will be a parameter that I'll be passing, which will be parent. So who will be the parent of 2? Which is 1. What does this mean? It means that I'm coming from 1. So I'm coming from 1. That is why the parent is 1. So I see that who are the neighbors of 2? It is just 1. Who is actually the parent. So does this lead to a cycle? No. I'm not going to visit 1 again because it is already visited. It is the parent. I don't care. Just going ahead with it. Coming back to 1, we will now go to the other neighbor, which is 3. Now when we go to 3, again we will mark who as the parent. We will be passing what as the parent. We will be passing 1 only as the parent. We are coming from 1. Right? So now we see from 3. Okay, 1 is the only neighbor. That is also the parent. So it does not lead to cycle. Done. Now we have visited all the nodes in this connected component, right? So 1, 2 and 3 are marked as visited. It is done. Now the thing is that still there is a cycle in this entire graph, right? So there is a disconnected component. Why I have drawn like this is for you to understand another very important point, which is basically that there can be disconnected components. So when you are detecting cycle, you should be trying to do DFS or BFS, basically any traversal, over all the nodes. Because it is possible that there are still a few nodes that have not been visited. So basically when you start your traversal, you will have to go through all the nodes to make sure that you're visiting all the nodes or you're checking for all the cycles. So even though you started from 1 and you visited 3 nodes, but there's still some nodes that are left to be visited. Now from here we can be starting from anywhere. We can be starting from 6, 5, anywhere. Suppose we start from 4. Okay. So I come to 4, I mark it as visited. So this is visited. I come to the neighbors of 4, which is basically 5. By the way, when I start from 4, who will be the parent? The parent will be -1. Now when I come to 5, what am I passing the parent as? Now the parent is 4. Correct? The parent of 5 is basically 4 because that is from where I'm coming. So that is the parent. I see that, oh, neighbor, parent. I'm not going to visit it. Then I see, oh, 5 is also connected to 6. So I'm going to mark 6 as visited. And then I'm going to go to 6. Now in 6, who is the parent? From where am I coming? So the parent is 5. So when I come to 6, the parent is 5. Then I see who are the neighbors of 6. The neighbors of 6 are 4 and 5. When I come to 4, I see that 4 is visited. Now this is where the problem is, that 4 is visited and it is not parent. It is not where I'm coming from. That means there is a cycle. Understood? That it is visited, it is already visited, but it is not the parent. It is not where I'm coming from. Suppose it was marked as like 5 and 4. Suppose I had written like this. I would have ignored 5 because it is the parent. That is where I'm coming from. I would have checked 4 again. That okay. Now this is not the parent. It is visited. That means there is a cycle. So I hope this is completely clear. So two very, very important points that we covered. Number one is that we have to keep passing parent to make sure that we do not mark the graph as cyclic, or we do not detect a cycle just because we are visiting the same neighbor again and again from where we are coming. The second point is that the graph can be disconnected. Now, these are the questions that you're going to be asking to your interviewer, and you are going to be writing the code accordingly, that they can be disconnected components. And I need to say that do I need to start traversals from any other nodes that are not visited? So whichever nodes are visited, okay, cool, we would have considered the neighbors. If there are nodes that are not visited, we definitely need to do the traversal. We dry ran using DFS. Now let's do it using BFS also, so that you are completely clear with the concept. So one thing that should be obvious is that here also the problem of coming from the node, it will still be there. So we'll still need to mark the nodes as parent. We'll still need to pass parent. Why? Because here also, okay, let's dry run it and see. Okay, but it should be clear. But even if it is not, it's fine. Let's just start dry running and it will be clear. Okay. So now suppose this is a very simple diagram that I made. It's a very common example as well. Suppose I start from 1. Okay, I mark this as visited. Now in BFS, what we do is we go to the neighbors. Let's quickly look how the adjacency list looks like. So 1 is connected to 2 and 6. 2 is connected to 1 and 3. 3 is connected to 2 and 4. 4 is connected to 3 and 5. 5 is connected to 4 and 6. 6 is connected to 1 and 5, right? So suppose I start from 1. I marked it as visited. I went to the other neighbor 2. Now 2, I am marking it as visited. But now in BFS, how we do things differently is that instead of recursively going from 2 again, instead of going deep, we are going to go breadth-wise. Okay, so and I'm going to mark 6 as visited. So now that I've marked 2 and 6 as visited, I will start visiting now the neighbors of 2 and 6, right? So suppose I start from 2. Now you should be able to understand why we need the concept of parent, because here again we are coming to 1, which is already visited, right? But when I go to 2, I would have passed 1 as the parent, so it is okay if it is visited. And I will see is 3 visited. No, it is not visited, so I'll mark it as visited, right? Similarly, I'll go from 6, I'll go to 1. Oh, 1 will be the parent of 6, so okay. Then I will mark 5 as visited. Now from 3, I will see that 2 was the parent. I will mark 4 as visited. Cool, done, right? I will come to 5 and I will see that, okay, 4 is visited. Why? Our parent will be 6 because I'm going like this, right? So 6 is the parent, but 4 is visited. That means there's a cycle. So you do by DFS or you do by BFS, it is the same thing. Just in BFS, how things are different is that we go level wise or breadth wise. So we start from here, then we go to this level, then we go to this level, then we go to this level. Now in this level, what is going to happen is that we have already visited from here. So when we come and visit again from here, we will know that, oh, there is a cycle. So this is how DFS and BFS is different, that here we'll be visiting like this, we'll be visiting like this. In the end, we'll come and visit the same thing again. But very important point that we have to keep passing the parent as well. Now that we have understood that in undirected graphs, we can do using DFS and BFS, let's see how would it be different for directed graphs. Look at these 3 graphs. Now this is a very, very interesting concept, guys. This will blow your mind. Be very, very focused. This is very interesting. Look at these 3 graphs and tell me how they are different. Firstly, tell me which all of them have cycles, right? So this has cycle. We all can agree to that. This is a cycle. Now this is also a cycle, right? So there's an edge going like this and there's an edge going like this. But is there a cycle? Is there something like this or like this? No, right? So this does not have cycle, but these two have cycles. So what is the difference between this and this? Let's see. Okay. So in order to understand that the solution that we talked about, whether BFS or DFS for undirected graphs, will it work for directed graphs or not? This is a very, very good example to take. Let's quickly number the nodes. So suppose it is 1, 2, 3, 4, and let's make the adjacency list. So 1 is connected to 2. Now 2 is not connected to 1. It is unidirectional. Like you cannot go to 1 from 2. Correct? That happens only in bidirectional, or you can say unidirectional graphs, right? Over here, From 2, you cannot go to 1, you can go only to 3, right? So you have talked about this edge, we have talked about this edge. Here we can go from 1 to 4 also, and we can go from 4 to 3. So there are only 4 edges, so 1, 2, 3, 4. Just remember that this is not bidirectional. Here you cannot go from 2 to 1 or from 4 to 1. Similarly, you cannot go from 3 to 2 or 3 to 4, right? Now let's see that would the solution that we did for unidirectional graphs work here or not. We start from 1 and we mark it as visited. 1 is visited. We go to its neighbor 2 and then we see, oh, the neighbor is basically 3. Okay, I'm doing DFS right now. So the neighbor is 3. And then we say that, okay, fine, we mark 2 is visited, we mark 3 is visited. So this is done, right? Then once we are done with 1, 2, 3, we see who was the other neighbor of 1. Oh, it was 4. Now I start from 4 and I see who is the neighbor of 4, which is 3. Now see that 3 is visited and 3 is not the parent, because where did I go to 4? I started from 1. So for 4, who is the parent? Parent is 1, correct? 4 ka parent is 1 because we went like this. But when we go from 4 to 3, 3 is already visited. So it is visited and it is not the parent. So does that mean that there is a cycle? Look at this like this. So there was one path and then you marked these as visited. When you came via another path and you saw that, oh, this is visited, you saw that, oh, there is a cycle. Why this worked for unidirectional is because, it was basically bidirectional. So if you come from this path or you come from this path, even if you come from this path, you can actually go back also, right? Versus over here, there's a restriction. You're coming from this path. But if you come from this path, that does not mean that there is a cycle. So this is a very, very interesting case. I'm saying this again. We dry run using DFS, right? Let's quickly dry run using BFS also so that it's completely clear. So there is 1, 2, 3 and 4. So from 1 we can go to 2 and 4. From 2 we can go to 3 and from 4 we can go to 3. If we do BFS also, what is going to happen? We mark 1 as visited. Okay. Then we mark 2 as visited and we mark 4 as visited. The parents of 2 and 4 would have been 1. So now once we are done with 1, we go to 2 and we see, okay, we are going from 2 to 3. We marked 3 as visited. The parent was 2. Then we go from 4 to 3. Now, this is already marked as visited and it is not the parent. The parent was 1. So what do we see? We see that there is a cycle, which is wrong. Correct? So I hope what you have understood till now is that the solution that worked for undirected graphs will not work for directed graphs. Right? Why will it not work? Because if there's a path like this and if there's a path like this, then you might mark it as visited again. Right? So what do we have to do differently for directed graphs is what we are going to discuss now. Let's now try to understand how can we solve this problem for directed graphs. Now you can see I have made both kinds of graphs over here. This one has a cycle. This one does not have a cycle. This was the problem that we talked about, right? So there's one path from here. There's another path from here. We are visiting this particular node from two paths, because of which we are saying that our previous solution is not going to work. So now think about it. How can I tweak the solution? My problem over here is that if I have visited from one path and I'm visiting from another path, I should not mark it as the cycle again, right? Now think about it very, very carefully. What if instead of just marking the nodes as visited, I have one more state of a node, which is visiting, which is the current path. So all the nodes that are there in the current path. So the thing is that if I am visiting in the current path, then it is okay. Then there's a cycle because it is the current path. But over here, if this was one path, this is another path, then it is not going to be a cycle. Correct? So now instead of just marking the nodes as visited, there were earlier two states, right? One was unvisited, which is basically the initial state. Then we kept marking as visited. Instead of that, what if we keep one more state, which is visiting, right? Now, there are a lot of people who are going to write this particular code or explain this in completely different ways, which is fine. The concept is same. Some people will explain it by coloring. Some people will say that, unvisited is going to be colored white. Visited is going to be colored black. And maybe the visiting ones, the path that you are in which right now, you will mark them as red. It's the same thing. You put flag, you color it, whatever you want to do, you can do. It's essentially the same thing. Let's try to see that how can we solve this problem using this one extra flag or one extra set or one extra array. The question that you must be thinking is that when do I mark a node as visited and when do I mark it as visiting? Whenever you are in a particular path, all the nodes in that path are in visiting state. If you are done with all the neighbors of that particular node, then it is visited. Okay, let's do using DFS for now. Suppose I start from this one. Okay, I mark it as visiting. Okay, so visiting is my color. I put 1 inside this. Then I go to 2. I mark it as visiting. I go to 3. I mark it as visiting. Okay. Now what happens is that 3 is done. Are there any other neighbors of 3? No. So I mark 3 as visited. Are there any other neighbors of 2? No. Visited. Are there any neighbors of 1? Yes. I'm going to start from 4. Okay. And as I mark these as visited, what am I going to do is I'm going to unmark them from visiting. Why? Now only 1 is there in the visiting. When you're done with all the neighbors and when you put it to visited, so the state can be only 1. Think of it like you can color it only with one color. Either it can be visiting or it can be visited. If it is in the path right now, it is visiting. If you are done with all the neighbors and everything, it is visited. Okay, so currently 2 and 3 are visited and 1 is in visiting. You come to 4, you mark it as visiting. You come to 3 and then you mark it as visiting. You see that 3 is visited, but is it in visiting? No. So is there a cycle? No, there is no cycle because it is not in the current path. So this works. So this is how we are going to solve this problem. Is it going to work for this graph also? Is it going to be able to detect the cycle? Let's see. So if we come to this particular graph, okay. So here again we are going to have two sets. One is visited, one is visiting. We are going to start from 1. 1 is in visiting. We go to 2. 2 is in visiting. We go to 3. 3 is in visiting. We go to 4. 4 is in visiting. From 4 we go to 1. Now 1 is still in visiting, right? Because it is still in visiting. We have not come back this path. Maybe there was, say, another neighbor of 1. Even if there was not any neighbor, we have not tracked back. We are still in the path. We are still visiting. So that means there is a cycle. If it is still, a bit unclear, it is fine. When we write code, when we dry run more, it will be clearer. But whenever you get stuck, this is a very, very good example to take. That one path, another path. This is one and then there's another one that you actually make the cycle. So try dry running using this. Take 2 arrays, visited, visiting. We will be writing code. In the next video, we will be first writing the code for undirected graphs using DFS, BFS. Then we'll come to this. Make sure you share it with your friends. You have no idea how much it will mean to me. Let me know in the comments that you have understood or not. If you have any doubts, I would love to clear it in the future videos. And I'm here to help you out in any other way. But please to make the effort. Please to subscribe. It would mean just so much to me. See you next time.